So in order to avoid this effect, we define joint central moments, right? We first of all shift each distribution by their means. So we have zero mean distributions essentially, and then obtain joint moments on these. Okay, so x minus its mean to the power j, x2 minus its mean to the power k. The definition is exactly the same except for these expressions here, of course. But here you see when you set j equals 2, this one, and k equals 0, you just have the square of this, which gives you the variance of x1. On the other hand, if you set j equals to 0, so this disappears, and k equals to 2, you have the square of this term here, which gives you the variance of x2. So similar to in the single random variable case, like the variance is a central moment, here we have central moments defined in a more general sense. Again, we can generalize these to higher orders, not only x1, x2, but x1 up to xn. The definitions are exactly the same. Okay, so regarding two random variables, the joint central first order moment is the covariance. So that is equal to j equals 1, k equals 1 case with joint central moments. The expected value of the product of x1 minus its mean and x2 minus its mean. So this is more of a much more sensible definition of, let's say, a measure of resemblance, because, well, you would now have, since you shift the distribution, the large values mean, or the positive values mean you are above the mean, negative values mean you are below the mean, etc. So when they are both positive together or both negative together, that means they are behaving sort of similarly. Okay, so covariance measures how x1 and x2 vary together around their means. Now observe this, when you actually start with the definition and expand this, you get x1 times x2 minus this expected value of x1 times x2 minus x1 times this expectation of x2, and then you have these two terms plus expected x1 times expected x2. If you remember, due to the linearity of expectation, I can separate each of these four terms, and you have this correlation minus this plus this. Now this I have written directly because the product of these two expectations is just a number. It's not random, so I can take it out of the expectation. Similarly, here you see expected value of x1 times x2. So this is x2 scaled by the mean of x1, but the mean of x1 is just a single value. So I can take it out of the expectation to obtain this, similar with this term. So this term and this term cancels out. What I have is covariance between x1 and x2 equal to correlation between x1 and x2 minus the product of their means. Okay, well, this is sort of a generalization of the relationship we have seen before that relates the second moment to the variance. So correlation resembles the second moment, and covariance in that sense resembles the variance. Okay, so this is sort of a generalized relationship here. But we do not generalize this to higher order dimensions, so there is no such thing as the covariance between x1, x2, and x3. Okay, and we will talk about covariance and correlation matrices later on. Now, covariance also, well, as we had said, correlation is affected by the means, but on the other hand, covariance is affected by variance. Okay. Scaling a random variable affects its covariance, similar to variance. If you remember, if you scale a random variable by a number greater than 1, what you are doing is you are dispersing the distribution, you are widening it, so the variance gets larger. But if you multiply it with a number less than 1, you are sort of, if you have this distribution, then you would have something like this. You are like squeezing it down. Okay, then the variance gets smaller. The effect is also present in covariance. Therefore, we say that covariance is not an absolute measure. Even if you have very similar distributions, when their variances differ on different scales, like one a multiple of the other, the covariance will be affected by this. So in order to also avoid this effect, we define the correlation coefficient between x1 and x2 as the covariance scaled down by the product of the standard deviations of x1 and x2. Okay, and by definition, whenever this correlation coefficient turns out to be zero, we say that x1 and x2 are uncorrelated. Okay, of course, this also implies the covariance is zero, but not the correlation to be zero. So this is somewhat misleading terminology. Uncorrelated doesn't mean correlation is zero. Uncorrelated means covariance is zero or correlation coefficient is zero. Again, it's sort of misleading that the correlation coefficient is defined in terms of covariance, but not correlation. Okay, so be careful about this. Or if you like, you can write this as the correlation minus product of the means divided by standard deviations. Okay, that's another way to see it.